Today's lesson: bond dissociation energies of halogens. In this lesson, we are going to learn why bond dissociation energy is different for different halogen. So let's begin. Halogens belong to column 17 in the periodic table. Fluorine, chlorine, bromine, iodine, astatine, tennessine. Astatine and tennessine are radioactive elements. That is why astatine and tennessine are kept out of consideration. Now let us see fluorine, chlorine, bromine and iodine. We know that from top to bottom along a column, atomic size increases like this. This is iodine, fluorine, chlorine, bromine, iodine. Atomic size increases from top to bottom along any column in the periodic table. Again, halogens are diatomic molecules. These molecules can be showed in this way: fluorine, chlorine, bromine, iodine. Bond dissociation energy of iodine molecule is 213 kilojoule per mole from bottom to top. From bromine, this is 224 kilojoule per mole. For chlorine, this is 242 kilojoule per mole. From bottom to top, bond dissociation energy increases. But in case of fluorine, bond dissociation energy is 158 kilojoule per mole. That is, for chlorine, bond dissociation energy decreases all of a sudden. Graphical representation may be like this. Along x-axis, bottom to top. Along y-axis, bond dissociation energies. Initially, it increases from bottom to top: iodine, bromine, chlorine. All of a sudden, it decreases for fluorine, iodine, bromine, chlorine, and this is for fluorine. For fluorine, it changes abruptly. But why? This is what we are going to learn today. Let's go to the detail. Bond dissociation energies of halogens. Molecule formation of halogen molecules. Molecules are expressed generally by X2. For fluorine molecule, F2, chlorine Cl2, bromine Br2, and iodine I2. Let us see formation of fluorine molecule. Fluorine, atomic number 9. Electronic configuration is 1s2, 2s2, 2p5. Let us see electronic configuration of fluorine in the box method. Outermost electronic configuration 1, 2, 3. This is 2s, 2px, 2py, 2pz. 2s orbital contains 2 electrons. 2p orbitals contain 5 electrons. 1, 2, 3, 4, 5. Here we see that 2pz orbital of fluorine contains 1 electron. This 2p orbital with 1 electron overlap with another 2pz orbital of another fluorine, and fluorine molecule is formed. This can be shown in this way. 1, 2, 3. 2, here 2. 2 electrons. 2s, 2px, 2py, 2pz. Another fluorine atom. Fluorine atom, fluorine atom. 2pz, 2pz overlap, and covalent bond is formed between 2pz, 2pz overlap. 1 electron, 1 electron. So these 2 electrons are covalently bonded electrons. This fluorine atom contains 3 pairs of electrons. 1, 2, 3. This fluorine atom contains 3 pairs of electrons. 1, 2, 3. This is molecule of fluorine. Similarly, chlorine molecule. Lone pairs of electrons, bond pair of electron, and lone pairs of electrons. For bromine, bond pair of electrons, lone pairs of electrons. Lone pairs of electrons. For iodine, bond pair of electrons, lone pairs of electrons. Formation of halogen molecules. Now let us see why bond dissociation energy is different for different halogen molecule. Already we know that fluorine is smaller in size, then chlorine is a bit bigger in size, bromine is more bigger than chlorine, iodine is, we can consider, biggest here among these 4 halogens. Now we can see in this way: fluorine, another fluorine atom, it contains 3 pairs of electrons. Then chlorine is a bit bigger, bromine is more bigger, and iodine is biggest here. For iodine, iodine atom contains 3 pairs of electrons. Here, what is covalent bond? This bonding pair of electrons, negative in charge. attraction between nucleus and covalently bonded electrons. Attraction between nucleus and covalently bonded electrons. This attraction is covalent bond. Here, this is the distance between nucleus and covalently bonded electrons. In case of iodine, iodine is bigger in size. That is why in this case distance is comparatively higher, then attraction becomes lower. More distance, less attraction. Less attraction, bond dissociation energy will be lower. In case of bromine, this is iodine, this is iodine. In case of bromine, the distance between nucleus and covalently bonded electrons is a bit lower compared to iodine. So here distance is a bit less compared to iodine molecule. Less distance, attraction is a bit higher compared to iodine molecule. Attraction higher, bond dissociation energy will be a bit higher compared to iodine. And that is the reason for iodine this is 213 kilojoule per mole, but for bromine this is 224 kilojoule per mole, a bit higher than iodine. In case of chlorine, this distance is more lower compared to bromine and iodine. Here, less distance, then attraction is more higher. Bond dissociation energy will be higher than bromine and then iodine. That is why in case of chlorine, bond dissociation energy is higher, and this is 242 kilojoule per mole. But in case of fluorine, in this case distance is more lower. Distance, least distance. That is why attraction should be higher and bond dissociation energy should be higher here, but less attraction, less bond dissociation energy. But why? In this case, lone pairs of electrons come closer, and here repulsion increases. In this case, repulsion dominates attraction force between two nuclei. That is, repulsion becomes dominating than attraction. That is why ultimately breaking this bond, fluorine-fluorine bond, becomes easier, and that is why in this case bond dissociation energy is the least, that is 158 kilojoule per mole. In case of chlorine, lone pairs of electrons are present, but in this case, lone pairs of electrons remain at more distance compared to fluorine. That is why for chlorine, bromine and iodine, repulsion is not key factor. In this case, attraction between covalently bonded electrons and nuclei is the key factor for chlorine, bromine and iodine. But in case of fluorine, repulsion becomes key factor. Repulsion dominates attraction force. Because of this, fluorine-fluorine bond weakens. That is why less energy is required, 158 kilojoule per mole. 2 points here. Distance between nucleus and covalently bonded electrons. Another point is electron pair repulsion. For fluorine, repulsion becomes dominating. For chlorine, bromine and iodine, attraction becomes key point. So, order of bond dissociation energy will be like this. For chlorine, this will be higher. For chlorine, 242 kilojoule per mole. For bromine, this is 224. For iodine, this is 213. For fluorine, this is 158 kilojoule per mole. So, order of bond dissociation energy will be like this: chlorine, bromine, iodine, and then fluorine. This is all about bond dissociation energies of halogens. No more today. Thank you very much.